Hello dear student, here I am Dr. Amjad Ali, and in this video we are going to learn the second assumption of error term, that is variance of error term is constant, and when the variance of error term is constant, this is known as homoscedasticity, and when the variance of error term is not constant, then we call it a heteroscedasticity. Okay, let's we give a detailed discussion about when the heteroscedasticity is existed, then what happened to our estimated results. Okay, let's discuss first the meaning of homoscedasticity or heteroscedasticity. Both heteroscedasticity and homoscedasticity are Greek origin word, and when we split these words into two parts, first having a Greek word homo, which mean same or equal. And when you are talking about the hetero, and the meaning of the hetero is different, are unequal. Okay, the second part of of the both word is same, that is sedasticity or sedasticity. Okay, some books pronounce it as sedasticity and some sedasticity. Okay, when we are talking about the second part of the word, that the same part of both words, that is sedasticity, that meaning spread or scatterness, or when you have the data, what is the quantity of spread in the data, and what is, how much scatterness in your data. Okay, so this means that homoscedasticity mean equal spread or equal scatterness. But when we are talking about the heteroscedasticity, this means unequal spread or unequal scatterness. Okay, for the measurement of scatterness in our data, normally in econometric we use variance. So now we can understand the meaning of the homoscedasticity or heteroscedasticity. When you are talking about the homoscedasticity, when we have the equal variance, and when we are talking about the heteroscedasticity, and this means there is unequal variance. So when we are talking about the homoscedasticity, we use this notation, that variance of error term is sigma square. It means that variance of error term is constant. And when we are talking about the heteroscedasticity, so this doesn't mean when we have to use a unequal sign here. We can use a subscript I in sigma square. So this is known as the variance of error term is not constant, so we call it a heteroscedasticity. So here we have a constant mean, homoscedasticity is constant variance, homoscedasticity, and we have a not constant mean, that is heteroscedasticity. Okay, there is a further discussion about the meaning of the homoscedasticity and heteroscedasticity. It has been assumed that the variance of error is constant. This is the assumption of error term. So this is known as the assumption of homoscedasticity. And if the error term do not have a constant variance, they are said to be heteroscedasticity. Okay, for better understanding of heteroscedasticity, suppose a regression has been estimated, and the residual, we have estimated residual u hat has been calculated and then plotted against one of the explanatory variable like x2t. We have multiple linear regression, and when we use ut is a dependent variable, and we are going to plot this with this, and if there is any type of trend between these two, then we can say that the variance of error term is not going to be a constant. So let see the shape, or we can say that the shape of the graph will give us the idea that there is a homoscedasticity or there is a heteroscedasticity. Okay, let's see the graphical presentation, that we have an independent variable x2, and we have here we are using a ut as on our y-axis. Okay, here we have some outcomes of ErrorTerm and independent variable. We will see here we have a trend with the independent and dependent variable. So this reveals that the variance of the ErrorTerm is not constant, although the mean value of the ErrorTerm is constant, but the variance is not going to be constant. So this shows that if the data shows this type of trend, we can say that there is a heteroscedasticity in our data, and no, our assumption is not follow the constant variance. Okay, this is clear evident that the error in the figure are heteroscedastic, that is, although their mean is roughly constant, but their variance is increasing systematically with increasing independent variable. As the independent variable is increasing, see the error term value is also increasing. When the independent variable decreasing, the error term value is also decreasing. So this is known as the variance is also going to change as the error term is moving from one observation to the other observation. Okay, let's discuss the reasons of heteroscedasticity. There are a number of reasons of heteroscedasticity, but here we are going to discuss the main or some important reasons of or causes of heteroscedasticity. Okay, let's say the first one, the outlier. You know when we have a few very higher values or a few very lower values, then this will create consider the outlier in our data, and the outliers urge our data to be towards the non-constant variance. So let's see in the graphical presentation that we have here we have a independent variable and dependent variable. Okay, when we draw the independent and dependent variable in a graphical presentation, see here we have a very high value, x is very high value and y has a very low value, and here y is very high value. So these 2 points are outliers. So these 2 points will force our variance to be not constant. So that's why the outliers are main reason of heteroscedasticity in our data. So in statistics we learn how to deal with these type of outliers. Okay, due to wrong transformation, sometimes you are transforming the data from actual to, let's say you have a data of y1, y2 and y2 and y2, y3 and y4, and you are going to convert this data into log form, and by mistakenly you are taking the log of y series, but by mistakenly you are not taking the log of y3 and you write it as it is. So this wrong transformation will create heteroscedasticity issue in our data. Okay, last one is the wrong specification or incorrect function form. Okay, you have a multiple regression model that y is equal to a plus bx plus x1 plus cx2 plus dx3, like that. You are taking 3 independent variables, and by fault, or you can say by lack of knowledge, you are taking x2 which is also decided by x3. So in this case x2 has no significant impact on y2, like that. So the best example is that if you are taking your university furniture and road accident, and relation, then regression will give you any type of negative or positive relation. But technically this is wrong specification. Technically they are theoretically this is wrong specification, that the university or school furniture doesn't have any type of significant or insignificant or theoretical relationship with roadside accident. Maybe the number of students have a direct relationship with these type of variable, like road accident. Number of students is increasing in the universities, that this may be have a strong or theoretical good relationship with the road accidents. But this internal variable which have no theoretical links, if you are taking as an independent variable, so this will create a heteroscedasticity issue in your data. Okay, detecting the heteroscedasticity is one of the main issue for everyone. Okay, there are two general ways to detect the presence of heteroscedasticity in the data. The first one is informal way. Informal way, the graphical method. And when you are talking about the formal way, that is a mathematical test or applied test, or you can say it a statistical test, and we will deal in detail about these type of tests in our coming session. Okay, let's discuss about the graphical presentation of the heteroscedasticity. Okay, if we have a y-axis on x-axis, either we have estimated x, or either we have an independent or explanatory variable, and on the y-axis we have variance, estimated variance here. Okay, keep it in mind that the Brooks always prefer that we can use the explanatory variable on the x-axis, but there are a number of books which are recommending that you can, for testing the heteroscedasticity, you can use either estimated y or your explanatory variable, either 1, 2, or 3. You have a 1, 2, 3, 4 independent variables, so you can use it as on x-axis, but you have to use the variance on the y-axis. Okay, let's see. We have some outcomes here. Okay, if this type of graph or this type of relation existed between the variance and the estimated y, or with the explanatory variable, then we can say that there is no heteroscedasticity in our data, because there is no relationship between the estimated independent or dependent variables, so there is no heteroscedasticity. If there is a relationship between the independent or dependent relationship, dependent variable with our variance, then we can say there is a heteroscedasticity issue in our data. Okay, let's see. We have another example that we have a dependent variable, estimated dependent variable y, or our explanatory variable on x-axis, and we have our variance on the y-axis, and we are going to draw graphical presentation. And if this type of graph can be constructed, then we can say that there is a heteroscedasticity existed in our data. So we cannot apply OLS or simple regression on this type of if this type of relation existed between these two. Here we have another example that we have estimated y, or explanatory variable, on x-axis, and we have a variance on the y-axis. Okay, if this type of relation existed between these two axes, then we can say that there is a heteroscedasticity existed between our error. So in this situation and in this situation, our variance is no more constant, and we cannot apply OLS or simple regression on this type of data. Okay, But in case of graphical methods, unfortunately, our researchers are rarely knows that the cause or the form of heteroscedasticity is so that is that a single plot doesn't give us the exact information or reveal nothing for us. So in this case, for example, if we are drafting, yes, let's see, here we are using here x1 or x3, and but uh, uh, but there is a exact relationship between x4 and x5, which is not included in graphical presentation. In this case, we cannot give exact relationship between the independent variable and our error term. So here we have the example. If the variance of the error term was an increasing function of x3, and researcher is using x2 in the graph with the error term, so he would be unlikely to see any pattern, and would thus wrongly conclude that the error has a constant variance. So under these conditions, graphical presentation is unable to explain the exact heteroscedasticity. Okay, it is also possible that the variance of the error term error change over the time rather than systematically. Here we are going to a systematically discussion, but sometimes the variance of error term change over the time with one of the explanatory variable. As one of the explanatory variable changes, the variance of the error is also changing. This phenomena is known as auto-regressive condition heteroscedasticity, and we will discuss this in a separate video. Okay, fortunately there are a number of formal statistical tests for the heteroscedasticity, and one of the simplest such method is Goldford 9065 test. So, okay, let's discuss the detail of this test. We have a Goldford quant 9065 test of heteroscedasticity. Okay, you can split the total sample data into two subsample of length t1 and t2. Okay, let's see here on the right side we have a data series of we have a one dependent variable and one independent variable. Okay, we have a 8,000 observation of y, and 8,000 observation of x, and we can distribute these sample into equal parts. Let's say we have a 4 for the t1 and 5 to 8 for the t2, and then we have to calculate the two residual variance from this series. When you have distributed this data into two parts, then you have to run the two separate regressions, and from these two separate regressions you have to find two residual variance, two error variance. Like first one, you can use this formula for the first error, like SI square. This is the variance formula. Variance is equal to u1 hat prime u1 hat divided by t1 minus tk, and this is for the second formula for the second variance. Okay, now we generate or develop our null hypothesis that the first variance of t1 is equal to the variance of t2. If these two variances are equal to each other, then we can say that there is homoscedasticity, and if these variances are not equal to each other, then we can say that there is a heteroscedasticity. Okay, then our alternative hypothesis is that the variance of the first variance is not equal to the second variance. Okay, and now we use the test statistic. GQ is simply the ratio of the two residual two error variance, where the larger of the two variance must be placed in the numerator. Keep it in mind, numerator from these two t1 and t2, which variance is is larger, we can use it as a denominator, and the smaller we can use it as a denominator. Okay, normally S1 square, you can say that the first variance is the higher variance for the sample length t, even it come from the subsample. So see here, sometimes we believe that this variance may be high, this variance may be high. So normally, when we have split the data into two parts, then normally S1, the first variance is normally have a higher value. But if this is not going to be higher value in any case, then you can use the denominator as it is. So here we can see the formula for the GQ. Okay, the largest variance divided by smallest variance. You can say it variance of first time period and the variance of second time period. Okay, for the F distribution, we can use the F statistic, that T1 minus Tk and T2 minus Tk. This is our degree of freedom when we are using the GQ test of heteroscedasticity. Okay, here is make the sensible decision. So keep it in mind that what is the conclusion when you are rejecting the hypothesis, and what is the conclusion when you are accepting the hypothesis. Okay, if the calculated GQ is greater than the critical value, normally we can say that when our calculated this part is greater than this part, so we can reject the null hypothesis. When you are rejecting the null hypothesis, to keep in mind there is a heteroscedasticity. But if GQ is less than, if this part, this is your calculated or estimated part, if this part is less than from this part, you can say a critical statistic, then you are going to accept this part null hypothesis. And when you are accepting the null hypothesis, then you have to conclude that there is a homoscedasticity in your data. So keep it in mind, when you are accepting the null hypothesis, there is homoscedasticity, and when you are rejecting the null hypothesis and accepting the alternative, then there is a heteroscedasticity in your data. So keep it in mind that in the presence of heteroscedasticity, we cannot apply simple OLS. Okay, there is another test that is very well known test, that is Y test, which is available in every software. Even you are using the eViews, so this particular test is available in software as well. Okay, let's discuss the steps available in or what we have to do for testing the heteroscedasticity in our data. Let we have a regression model. Y is equal to beta 1 plus beta 2 x2t plus beta 3 x3t plus ut. Okay, you have to run the regression from this, and from this regression line, we are going to find that either its variance is constant or not. This is our main ultimate objective. For this, we have to calculate our estimated error term, and you can say it residual, and run an auxiliary regression. Okay, for running another regression, you can use variance of error term as a dependent variable, and you can use x2, x3, x4 and x2 and x3 as independent variable, and the square of the x2 and the square of the x3 as independent variable, and the cross product or cross multiplication of x2 and x3 as an independent variable. Okay, after running the regression, this new regression, then you have to decide that either there is a heteroscedasticity or heteroscedasticity existed in our data or not. Okay, here we have the VT as another error term. Whenever you're running any type of regression, to keep it in mind that you have to introduce an error term in your regression line. Okay, if here we are introducing VT as a error term, so keep it in mind that VT is a normally distributed error term and independent of our dependent variable, and this is not related to our this dependent variable. Okay, this regression is the interpretation of this regression is that this regression is of the square residual on a constant. The the original explanatory variable, the square of the explanatory variable, and their cross product are used as an explanatory variable or independent variable here. So keep it in mind to see we are actually to see that why the square residual are the quantity of the interest. Recall that there is another random variable, or if there is another random variable, then our variance is not constant. So the variance can be written as, we have to write the variance of this regression line. The variance is equal to expected value of ut minus expected value of ut. If you are going to open this square, then we are very well aware that expected value of ut is equal to 0. If you are putting the expected value of ut is equal to 0 here, then only your variance is equal to u square. So this shows that the variance of error term is constant. So this is technically known as there is a homoscedasticity in this case, but this is the final formula for the. Okay, it is not possible, keep it in mind that in econometrics or in diagnostic tests especially, we cannot find the scale of the error of the for the population. So we have to rely on sample error terms. So that's more important, that we have to decide the heteroscedasticity or homoscedasticity decision on the basis of sample error. Okay, use F-test procedure for checking the presence of the heteroscedasticity in our data or not. Okay, we have see here we have alpha 1, alpha 2, alpha 3, and alpha 4, alpha 5, and alpha 6. So all the 6 alphas are tested for, and we have to develop the null hypothesis with all the 6 alphas here. Okay, these are all equal to 0, separately equal to 0, and for the null hypothesis that alpha 2 is not equal to 0, alpha 3 is not equal to 0, and alpha 4, 5, and 6 is not equal to 0. To keep it in mind that you have to make a sensible decision here. If you if the calculated F statistic is greater than the critical statistic, keep it in mind, we have to reject this. If our calculated F statistic is greater than this, than our critical value, then we have to reject this. When you are rejecting this, so there is a heteroscedasticity in your data. Keep it in mind that when you are rejecting this, so technically you are accepting this, and when you are accepting this, so there is a heteroscedasticity. Okay, if the calculated F statistic is less than the critical value, we are accepting the null hypothesis. So keep it in mind that we are accepting this. If we are accepting this, then there is a homoscedasticity in our data. So keep it in mind that the null and alternative decide that either homoscedasticity or heteroscedasticity in our data. We have to face one. Either we have a heteroscedasticity in our data, either we have a homoscedasticity in data. With if this is existed, this does not exist. If this existed, this does not exist. Okay, note here we have our note that in the presence of the heteroscedasticity, we cannot apply simple regression or OLS on our estimated data. Okay, consequences. Here are some consequences of the heteroscedasticity, and these consequences will urge us that we cannot apply OLS. And let's see the first. The estimated coefficient are maybe still unbiased, but they are no more blue, best linear unbiased estimator. Sometimes in the presence of heteroscedasticity we estimate the parameters, but they are not unbiased still, but they are no more best linear unbiased estimator, and you know the parameters properties, the parameter must be blue, best linear unbiased estimate. Okay, there is no longer minimum variance among the unbiased estimator. Either you have in the first case you have the unbiased estimate still, but they are not blue. When they are not blue, then the variance is not minimum, because our main aim of the regression is to minimize the variance. But if if there is a heteroscedasticity in our data, then the variance is not remain minimum, so variance is increasing. When variance is increasing, then we cannot apply OLS on such type of data. Okay, variance sigma square error variance does not appear in the final estimation of the coefficient. You are very well aware that when you get the estimates in eView, then the variance, standard deviation, or different type of diagnostic outcomes are given beneath the table of the regression results. So if there is a heteroscedasticity data, then keep it in mind that the variance of error is not appearing in this list. So technically these results are not good for making any type of policy. Okay, coefficient of standard error no longer hold for further testing. So keep it in mind, when there is a heteroscedasticity, the coefficient of standard error which is used for further testing, that you have to use the standard error for testing the t-test and for testing f-test. So if there is a heteroscedasticity, so standard error is not a good estimate for the t-test and for the f-test. Okay, the estimated inferences become misleading. We cannot forecast on the basis of these findings. So keep it in mind that when there is a heteroscedasticity, you cannot make any type of inferences, because these inferences are misleading, and you cannot give government or businesses or your organization any policy on the basis of these findings. Okay, standard error of slope will be too low for justification of coefficient, where standard error of intercept is very high. So keep it in mind that when you have a heteroscedasticity in your regression model, then your intercept standard error is very high, but your slope standard error is very low. So these consequences make the estimated outcomes simply, you can say, biased. So biased estimates are not fruitful for the policy implication or for the forecasting point of view. Okay, dealing with the heteroscedasticity, this is more important, that how can we deal with we can reduce the heteroscedasticity and the data. The first okay, if the form of the heteroscedasticity is known, then you can use the GLS to remove the heteroscedasticity. But first you have to know that what type of positive, negative, or what type of heteroscedasticity is existed. Either this is existed because of outlier, either this is existed because of incorrect function form, either this is existed because of wrong transformation. So you have to keep it in mind that what type of heteroscedasticity existed. So suppose that the variance, the error variance was related to ZT by the expression, and you have the variance of error variance of error multiplied by ZT square. Okay, keep it in mind that here ZT, if your if this part of ZT square has not existed in this equation, then in this formula, then our variance of error term is constant. But we see that after some formulation that any digit ZT is creating unequal spread or unequal variation in your in your variance, then you have to multiply this digit with your variance. Okay, all that would be required to remove the heteroscedasticity would be divided the regression equation through by zt. Now we have a regression equation and we have to divide zt by all of the variables here. Okay, let's see, we have a yt divided by zt, and here we have a beta 1, but we are not dividing zt by beta, and beta 2 we are dividing by zt by x2, and like that x3. Okay, here vt, the interpretation of vt is more important here, that vt is the combination or you can say the vt is generated from the ratio of ut divided by zt. Okay, this means that now our error term is white noise, because now our error term is zero mean with constant variance. Okay, if we have a variance like this, we have a variance is this, then after dividing, and now see it carefully, that variance is equal to variance ut divided by z, and when you multiply by this variance, then this is called the u square, and when you multiply by this is called the z square. So see it, variance of u divided by z square. Okay, this variance u we have, suppose here, is equal to sigma square z square t. So we have to put the its value here. So then z square is cancelled out by z square, and then we get sigma square. So this transformation enable us, GLS transformation enable us that now our variance is a constant. So we can say that generalized least square transform the data in such shape which satisfy the OLS assumption, and it is known as a weighted least square. We can say it as WLS, where OLS is unweighted method. Now we can apply OLS on this data after this transformation. However, researchers are typically unsure of the exact cause of heteroscedasticity, and hence this technique is usually infeasible in practice. So keep it in mind. Whenever you want to use the generalized least square method, you are familiar what type of heteroscedasticity existed in your data. Without such information, you cannot apply GLS. I have found many students that without any prior fulfilling the assumption of GLS, they can apply the GLS. So keep it in mind when you are very well aware the what type of heteroscedasticity exists in your data, then you can apply GLS. Otherwise, you cannot technically apply the GLS. Okay, when we are talking about dealing with the heteroscedasticity, when you are talking about the dealing of the heteroscedasticity, that the first one, transfer the variable into logs or reducing by some other measure of size. This has the effect of recycling the data to pull in extreme observation. The regression would then be conducted upon the natural logarithm or the transform data. Keep it in mind, when you have a higher number of observation in your data, then and there are few observations which have a lower value. In this case, there is a chances of heteroscedasticity. So you have to take the log of the whole series, and this will reduce the variation in the data, and your variance become equal, and there and you can say there is a homoscedasticity in the data. Moreover, when you are using the absolute data, you can transform this data into growth rate form, then the heteroscedasticity issue can be resolved. Okay, in this case the regression would be then conducted upon any it's mean that you have to use the transform data for your regression analysis. But here one of the big issues that when you are using the logarithm or log for transforming the data, but if your some observation has zero value or some observation have negative value, then you cannot apply log form, because in this case the log cannot be applied. If you have a zero, some observation are zero, some observation are negative, then log transformation is not possible mm, to apply. So under this condition you have to use the heteroscedasticity consistent standard error estimate. Most standard econometric software packages like you have eViews have an option that allow the user to imply standard error estimate that have been modified to account for the heteroscedasticity following white. You have the white test which is best known for removal of the heteroscedasticity, and this is available in eViews. We have to practice it in our eViews session when we conduct a eView session of heteroscedasticity. Okay, there are some other computer-based tests for the removal of heteroscedasticity, like we have a park test, we have a Spearman rank correlation test, we have a angles auto-regressive conditional heteroscedasticity, and some of other tests which are used for the removal of heteroscedasticity in the data. And when you remove the data heteroscedasticity in the data, then we can apply OLS on this data. But without the removal of the heteroscedasticity data, we cannot apply OLS on this data. Okay, this was the heteroscedasticity discussion. I hope you enjoy it, and in coming video we will discuss another assumption of error term. Okay, see you, ciao.